Okay, so what I'm going to do in this video is run through a derivation of the Lorentz equations. And the Lorentz equations, from the Lorentz equations is where you get your time dilation and length contraction. So we're going to start with these two postulates. And this part is really important. So the laws of physics are the same in all reference frames moving at constant velocity, that is to say inertial reference frames, and this is the principle of relativity. Second postulate is simple: the speed of light is constant. So we're going to do what Einstein did, which was assume that these two postulates are true, and we're going to find out what would logically follow if these two postulates are true. And so this is the most important part to remember, that what we're doing is asking ourselves, what would logically follow if these two postulates are correct, if they are true? And so the following arguments are going to be quite subtle, or some of them will be, so you'll have to follow quite closely and probably spend a bit of time just thinking about it. But what's most important is if you can follow the logic of the arguments that are set forth rather than necessarily the mathematics, though the math is just algebra. So we're going to start with this page here. So we have a light signal which is proceeding along the positive x-axis in a system of coordinates, that is to say a reference frame, which we'll call K. So we're just giving this reference frame a name, basically, a label. We could call it, for example, well, let's think of it as the platform on a train station. So we could call it, every time we could call it the platform of a train station, but that's a bit cumbersome, so we just call it K to make it easier. So we'd say an observer in K would be a person standing on the train station platform. Okay, so a light signal which is proceeding along the positive x-axis in a system of coordinates, which we'll call K, is transmitted according to the equation x equals ct. So c is the speed of light times the time. So you might have seen a similar formula, something like delta x on delta t is equal to velocity. This is the same equation, it's just rearranged, right? So we've got our t on this side, v is equal to the speed of light, and our x on this side. And so we could rearrange that. We could just take the c times t over to this side, and so we'd end up with x minus ct equals 0. Okay, so now we're going to think about our other coordinate system or reference frame. So in another coordinate system, which we'll call k primed, so this time we can think of k primed as being a train, and let's call it an express train that is passing through the train station without stopping, and it's moving at a constant velocity. So in another coordinate system, which we'll call k primed, our train, moving with constant velocity v relative to k, we have, for the same light signal, so by the way, having this little dash up here is just called primed, so that's why I call it k primed. And so this is x primed, this is t primed. So for the same light signal, we'll have x primed minus c times t primed. Same as we had up here, except we've changed our coordinates to the primed system, which is, if we're thinking about it in more physical terms, we can think about it as a train. And so an observer in our k primed system would be a person on the train, say, watching the platform whiz by as the train goes past. So, therefore, we can say this, and that's because this equation here is equal to 0, and so is this. This is equal to 0. So these two must be equivalent. And what we can do is also put in this h, which is just a constant. So it won't actually change this. Multiplying 0 by a constant doesn't change it. So we're allowed to just chuck a constant in here too. Okay, so let me shift the page up. So like I said, where h is some constant, this must also be true. So, for a light ray being transmitted along the negative x-axis this time, because before we were going along the positive x-axis, we obtain a similar equation, except we just have pluses here now instead of minus signs. So the argument is exactly the same as what we had up here. We'll just have plus signs here instead of minuses. And this u, again, is a constant. Okay. So, if we add equations 1 and 2, which are these two equations, I've labelled them here 1 and 2, the t primed part will cancel out, leaving us with an expression for x primed. So notice there's a minus sign here and a plus sign here, so these terms will cancel out if we add them. If we subtract equation 1 from equation 2, or vice versa, the x primed part will cancel out, leaving us with an expression for t primed. So we can get an expression for just x primed and t primed if we both add and then subtract these two. So we'll do that now. We'll do the addition first. So we have here equation 1 plus equation 2 gives us this. So x primed plus ct primed from equation 2 and plus x primed minus ct primed from equation 1 is equivalent to the right hand sides of these equations added together. So h times x minus ct plus u times x plus ct. And so we can expand some of that out. So here our ct primes will cancel, leaving us with just two x primes, sorry. And then if we multiply these constants out, we'll get h times x minus h times ct plus u times x plus u times c times t. And now we can have a look at this, and we can see that we have our two x terms. We can pull an h and a plus u out times our x, so we can factorise this. And our ct terms, we have u minus h, so we can write that as u minus h times ct. We still have 2x primed over here. Okay, so at the bottom of the page. Then from that, so I'll shift this one up. So once we go there, all we can do now is just divide both sides of this by the 2, so we just get x primed over here by itself. And we'll end up with h plus u, which are just two constants, remember, divided by 2 times x plus u minus h divided by 2 times ct. Okay, so now, get that one out of the way. Now we'll do the subtraction. Okay, so we'll have equation 2 minus 1. So in this case we have the left-hand side of equations 2 and 1. So we have x primed plus ct primed from equation 2 minus the part from equation 1, which was x primed minus ct primed. And that is equivalent to the right-hand sides of equations 2 and 1. So from equation 2, u times x plus ct minus the part from equation 1, which is h times x minus ct. And so again, following the same sort of structure, our x primes here will cancel out, they'll both be minuses, and we'll just be left with 2 ct primes. We can multiply our u through and our h through, and we get u times x plus u ct minus hx plus hct. So then we can factorise this again, so we'll have still 2 ct primed on this side. But from our x parts, we have u and a minus h, so u minus h times x. And from our ct parts, we have u plus h, so we have u plus h times ct. Again, we can divide both sides of this by 2, so what we end up with is c t primed equals u minus h on 2 times x plus h plus u on 2 times ct. Okay, so since u minus h on 2 and h plus u on 2 are just constants, we can simplify these equations. Notice that, okay, so here, see that? Yep. So we can say that h plus u on 2, let's just let that equal a because it's simpler. We don't have to write this is a constant, this is a constant, this is a constant. So the whole thing is a constant, so we might as well just write it as a constant like this, a bit easier to deal with. And then we can say h minus u on 2, let's let that equal to b. Notice that h minus u on 2 is the same as minus u minus h on 2. So I'm just following Einstein's notation here at the moment. Okay. So then what we have is, if we just replace these with a and b in our equations that we found, we'll end up with, so our equation for x primed was, we'll have this, so instead of, what did we have? So up the top here, we had x primed times h plus u on 2 is x. Now we're replacing that with a, and so we'll just get a times x. And we had u minus h on 2 times ct, so we'll replace that with minus b, because this here is minus this here. So we'll just replace that with minus b times ct. So that's what we have for our x primed. And then for our ct primed equation here, if we replace these with a and b, we end up with ct primed equals act minus bx. And that's from this here. Okay. So if we look at the origin of our k-primed coordinate system, moving at velocity v with respect to k, so what we're saying is we're looking at the origin of our train, the coordinate system that's attached to our train, which is our k-primed, moving at velocity v with respect to k, which is the platform, the train station. So if we look at the origin of this system in our train, this coordinate system, we have, so 0 on this side because we're setting, because this x primed is our x coordinate in our k primed system. We're looking at the origin, where that's where x primed equals 0, right? So we set that equal to 0. And we get this, a times x minus bct, same as up here, is equal to 0. So then we can rearrange this, a times x equals bct, and then we can finally get x equals bc on A times t. Now if we look at this, and if we go back to the equations we had for light, so remember we had this equation for velocity, delta x on delta t is equal to v. We could rearrange that to say delta x is equal to v times delta t. We've essentially got the same thing here. X is equal to, this is going to be v times t. And so, finding the page, of course. And so what we have is, therefore, v is equal to bc divided by a. It's over here. BC over A is equivalent to our velocity. That's the velocity of the train moving past our train station platform. So we can then say that the velocity of our train is equal to BC on A, or if you want to be more abstract, the velocity of the K-primed system with respect to K is V. And you can say it the other way around as well. You can say the velocity of the K system with respect to K-primed is also V. Because the person on the train sees the platform zooming past them, and the person on the platform sees the train zooming past them. Okay, so hopefully that's clear. If it's not, don't worry too much. Let's keep going. So, since a unit measuring rod, now this is Einstein's language, but you could think of this as just like a 1 meter ruler. So, let's say a 1 meter ruler at rest with respect to K, our platform, will be the same length as judged from K primed. This is quite a subtle point. So what he's saying here is that if we both have, let's say we both have a 1 meter ruler manufactured by the same company, and so just let's say I'm going to hop on the train and you're going to stay on the platform. So just before I hop on the train, we compare our 1 meter rulers, we put them up side by side. So if this is our 1 meter ruler, if this is mine and this is yours, say, we put them side by side and we double check that they're exactly the same length, and we know that. Then when I get on the train and I start moving, that 1 meter ruler, to me, it's still going to be 1 meter. I'm still going to read it, to measure it. If I take out a tape measure and measure it, it's going to be 1 meter to me. And while you're still standing on the platform, if you take out a tape measure and measure your ruler, it's still going to be 1 meter for you. So what he's saying here is this 1 meter ruler at rest with respect to K, so the 1 meter ruler that you're holding in your hand on the platform, you will judge it to be the same length as I judge my 1 meter ruler from the train when I'm standing on the train as it's moving. This is exactly the principle of relativity, that the laws of physics are the same in all inertial reference frames. So you might have to think about that a bit, because that's a really subtle point and it's kind of hard to get your head around. But let's continue. So in order to see how the points of the x primed axis appear as viewed from K, which is the platform, we only need to take a snapshot from K primed, We only need to take a snapshot of K primed from K at a particular time. Let's say t equals 0. So what we're saying here is, in order to know how the points of the x primed axis appear. So we could say what the length of my ruler looks like as viewed from your reference frame. What we need to do is take a snapshot from the train. Oh, I keep saying that. We need to take a snapshot of my ruler on the train that I'm holding from your reference frame. So you'll be standing there and you'll take, say, a picture of me flying by while I'm holding my ruler out so you can see it. And it doesn't matter what time we take that picture, anytime. We can, and just to make it simpler, we'll just say at time equals 0. That's your time equals 0. Then what we obtain is the following. So for our x primed equation that we developed just before, we'll have this. So here I've just written BC times 0 because our time, your time now, t is equal to 0. That's when we're taking the snapshot. And so we'll just have x primed is equal to ax minus bc times 0, which of course gives x primed equals a times x. Now, we say thus 2 points of the x primed axis separated by delta x primed equals 1. So this is just a distance. So if you had like 2 points on your x primed axis, say we just call them delta x2 and we'll call them delta primed 2 and say delta primed 1. So delta primed 2 minus delta primed 1, there are 2 points. That's equivalent to delta x primed. So all we're saying is that the distance, delta x primed is the distance between these 2 points in the x primed coordinates. So 2 points of the x primed axis separated by delta x primed equals 1. So we're just saying that this distance is going to, let's just set it equal to 1 because 1 is an easy number to deal with. 1 meter we could say, our 1 meter ruler. When measured in the k primed system, are thus separated in our instantaneous snapshot by the distance. So what he's saying is, measured in my system on the train, my ruler is 1 meter long. And they are separated in your frame by this distance. We've used this equation here, where we've set this x primed just equal to 1. So delta x primed, the distance from your reference frame, is 1 on A. So that's what you are going to measure my ruler to be as I fly past you in the train. Even though from my perspective, my ruler is equal to 1 meter. Now we don't yet know what A is. A is just a constant, but it could be 1. If it's 1, then there's no difference. You will still measure my ruler to be 1 meter, but we don't know what it is yet. So now we'll do the inverse, okay? So we're going to take a snapshot. I'm going to take a snapshot from the train as I fly past you guys on the platform. So, but if the snapshot be taken from k primed at t primed equals 0, and if we eliminate t from equations 3, taking into account equation, that should be 4, we obtain. So I've written again equations 3. These are just our x primed. See that? Yep. Our x primed and ct primed equations that we came up with. And 4 was what we came up with, the velocity of the two coordinate systems relative to one another. Okay, so I've just written them again there so we remember what they are. So now, we don't have to make a change to this one. But what we've got was, we said, now we're taking the snapshot from my perspective at time for me, when time for me equals 0. Again, this doesn't have to be time equals 0. Time equals 0 is just an easy, it just gets rid of the t primed here, so we don't have to deal with it. But this will work for any time. So we've set this t primed equal to 0, so now we get x primed equals ax minus bct, which we had before. 0 equals act minus bx. Now, what we'll do, so we've set t primed equal to 0. Let's make use of equation 4 by seeing if we can just rearrange it a little bit to get bc on a, so we can just write that as v. So in this equation, if we just divide by a, we'll get rid of that a here. Here, we'll have bc divided by a, which is what we want, because then we can just write that as v. And of course, on this side, we'll just have to put x prime divided by a. If we do something similar to this side, so how are we going to get this b to be bc on a? Well, we'll have to multiply by c and then divide by a. So if we do that, we end up with c squared, because we multiplied by c, and then divide by a, get rid of this a here, and we'll end up with a here, so we can just write that as v. And that is what we have here. Okay. So now all we've done is just substitute in v equals bca, where we had our bca's here, bc on a, sorry. So I've got x primed on a equals x minus vt, 0 equals c squared t minus v times x. So now we want to get these equations, we want to get t just on one side, because then we can eliminate t from the equations and just have something in terms of our x's and x primes. So let's do that. So I've skipped a few steps here, but basically what I've done, because I have a minus sign here, I just take this over to this side, move this one over to this side, so there'll be a minus sign there, and then divide all of it by v to get the t by itself. So we'll have t equals x divided by v minus x primed divided by a times v. Same thing here, move this over to this side, divide by v, move this over to this side, divide by c squared to get t by itself. We'll have t equal to v divided by c squared times x. So now, because this expression is equal to t and this expression is equal to t, these two expressions are equal to each other. So let's set them equal to each other. So v on c squared times x, this one, is equal to x divided by v minus x primed divided by a times v, this one. So now we can rearrange this and get our x primed on one side. And so again, I've skipped a few steps here, but what I've done, because I have the minus sign here, I just take it over to this side, and then I'll take this one over here, it gives me a minus sign here, and I'll multiply through by a times v, so that v will cancel, and I'll get an a here, and then I'll get an a and a v here, so I'll get minus a v times this bit, so it's going to be v squared on c squared times x. Okay. So we can factor out this a and x because they're in both of these expressions. So we'll just say a times 1 minus v squared on c squared times x. So all we did there was just factor out the a and factor out the x. Therefore, we conclude that 2 points on the x-axis, so this is your x-axis, separated by the distance 1 relative to k, so you measure your ruler to be 1 meter in your own system from your point of view, will be represented on our snapshot by the distance. And so this is going to be my snapshot of you now as you fly past me. It's going to look like, as I'm on the train, that you're flying past me. It's going to be delta x primed equals a times 1 minus v squared on c squared. That's because we set this delta x equal to 1. Now here is another subtle point. But under the assumption of the principle of relativity, these two snapshots must be identical. So what we're saying here, we find, so your snapshot of my ruler as I flew past you from your perspective was equal to 1 on A. Okay? So the length of my ruler from your perspective as you took a snapshot as the train flew past and I held my ruler out was equal to 1 on A. From my perspective, as you flew past me standing on the platform and I took a snapshot of your ruler, I see your ruler as being this length, a times 1 minus v squared on c squared. But under the assumption of the principle of relativity, these two snapshots must be identical. So again, what he's saying is that from my perspective, okay, so let's imagine as I fly past you on the train, I hold my ruler out, you take a snapshot, and you measure it to be, my ruler to be 0.8 meters. When from my point of view, you fly past me on the platform and I take a snapshot of your ruler, from my perspective, your ruler will also be 0.8 meters. Okay? Which means that this here is equal to this. It has to be equal to this under that assumption. So hence delta x in equation 5 must be equal to delta x primed in equation 5a, so that we obtain delta x, I'll keep that there actually, so you can see equation 5. So we'll just write it as delta x is equal to delta x primed, which means that 1 on a is equal to a times 1 minus. Okay, so from there, we can times both sides by a, so we'll have 1 equals a squared times this. So we can take this over to this side by dividing by this, and we'll get a squared is equal to 1 on 1 minus v squared on c squared. And so if we take the square root of both sides, we end up with a equals 1 divided by the square root of 1 minus v squared on c squared. And this should look familiar because this is just gamma, which is the Lorentz factor. Okay, so we're getting close to the end now. So the equations 4 and 6, 6 was the one we just determined, and here we have equation 4, so this is our equation for V, and 6 was our equation we just had for A. These two equations determine the constants A and B. So by inserting these constants into equations 3, we obtain the Lorentz equations. So remember equations 3 were these two here. So now if we insert our values for A and B into these two equations, we obtain the Lorentz equations, which is what we were looking for. So let's start with our x primed equation, which was x primed equals ax minus bct. So note from equation 4, which is v equals bc on a, we can get, if we just multiply both sides of this by a, we have bc equals a times v. And so that's what I've done here. I've let bc equal a times v. Okay? And since we know what a is, we just found out what a is. It's the Lorentz factor. We can write x prime equals a divided by 1, square root of 1 minus v squared on c squared, minus vt divided by square root of 1 minus v squared on c squared, which gives us this, x minus vt divided by this again, which is our first Lorentz equation. So this is telling us what the x coordinates in the k prime system, so what the x coordinates of, what my x coordinates in the train look like with reference to your x coordinates and your time coordinates. Okay? And for our other equation, our ct primed equation, we had this. We can use this fact again up here. So what we'll do is, because we've got a b here, we can say b is equal to a times v divided by c. So that's what I've done here. I've replaced the b with a times v divided by c. And so if we divide both sides by c, we get t primed. This c cancels, so we'll get a times t minus a times v divided by c squared, all times x. And so since we know what a is again, we can write in what a is, and that's going to give us these terms on the bottom here. And that gives us t primed is equal to t minus v divided by c squared times x divided by the square root of 1 minus v squared on c squared. Now, what's important to notice in both of these equations is that we have, so this is measuring distance in one reference frame, or you could think of it as space in one reference frame. That's equivalent to a mixture of both space and time in another reference frame. Okay? Time in this reference frame is equivalent to a mixture of both time and space in this other reference frame. Okay? So space coordinates and time coordinates are being mixed together. What looks like just time to me looks to you like a mixture of time and space. So I'm just going to end with this quote from Hermann Minkowski, who was one of Einstein's professors. Henceforth, space by itself and time by itself are doomed to fade away into mere shadows, and only a kind of union of the two will preserve an independent reality. So, hopefully that was clear. Again, don't have to worry so much about the maths. The most important point was that what we did was see what logically follows from assuming that these two postulates are true. And if you can follow the logic of what we just did, hopefully that will give you a bit more insight into how we end up with this mixing of space and time. And then the next video I'll show from these Lorentz equations how we can get length contraction and time dilation.